For the next couple of weeks, we're going to be learning about growth. We're going to start out in this section with geometric similarity. You might remember the concept of geometric similarity from geometry in terms of triangles. Two triangles are geometrically similar if they are the same shape, that is, they have all of the same angles, but they are different sizes. Then multiplying the lengths of the sides of one triangle by some number will give us the lengths of the sides of the other triangle. So you can see in my picture down here that if I take the sides of the smaller triangle and multiply their lengths by 2, then I'll get the lengths of the sides of the larger triangle. And this works for other shapes as well, not just triangles. Two objects are geometrically similar if they have the same shape, but they don't have to be the same size. So now I've got a puzzle piece shape. My smaller shape has a height of 1, and my larger shape has a height of 2. We can compare the sizes of two geometrically similar shapes using the linear scaling factor. The linear scaling factor L of two geometrically similar objects is the ratio of the length of any part of the second to the corresponding part of the first. So to get this ratio, we're going to divide the length of some part of the second shape by the length of the same part of the first shape. So here I've got the height in this case for my puzzle pieces. So to get my ratio, my linear scaling factor, I'm going to divide the height of the second puzzle piece, which is 2, by the height of the first puzzle piece, which is 1. And this tells me that my linear scaling factor L is equal to 2. I can also scale objects down as well as up. So I can make objects either larger or smaller. When any object is scaled with linear scaling factor L, the distance between any 2 points on the object is scaled by a factor of L. So you can see here that I've scaled down my large puzzle piece by a linear scaling factor of 1/3. So the height is 1/3 of the original height, but if I look at this green line, the length of that green line is also going to be 1/3 the length of the green line in the original shape. So we've been looking at lengths, but we're also going to talk about area. Area doesn't scale in the same way as length does. You can see here that 4 copies of my smaller shape fit into the area of the larger shape. So while my linear scaling factor here is 2, the area is scaled by a factor of 4. And in fact, the area of a scaled up object is going to go up in proportion to the square of the linear scaling factor L squared. So since L is 2 here and 2 squared is 4, my area is going to scale up by a factor of 4. Similarly, the area of a scaled down object is also going to go down in proportion to the square of the linear scaling factor. Anytime when my linear scaling factor L is less than 1, that means I'm scaling down. So in this case, I've got L equal to 1/3. Then my lengths are scaled down by 1/3, but when I look at the area, that's scaled down by L squared, so 1/3 squared, which is 1/9. So the area of my scaled down shape here is 1/9 the area of the original shape. And we can write this symbolically this way. So this little equation here means that A is proportional to L squared, so the area is proportional to or scales as the linear scaling factor L squared. So we've just looked at two-dimensional shapes so far, but we can also scale three-dimensional shapes. Here I've got a three-dimensional cube, which I've scaled with a linear scaling factor of L. So if the length of the sides of this small cube were 1, then I've scaled it up here, so the length of the sides of the large cube is 2. So lengths work the same, but what about volume in this three-dimensional case? So I want to ask the question, how many of the original cube can I fit into the new cube here? Well, I've got the sides of my new cube are 2, so I can fit 2 smaller cubes in each direction, up, down, and across. So in total, I can fit 8 copies of the smaller cube into the larger cube. And for any object, the volume of a scaled up object is going to go up in proportion to the cube of the linear scaling factor. So this is L cubed. So here, L is equal to 2, so when I'm looking at volume, L cubed is equal to 2 cubed, which is 8, so the volume is scaled up by a factor of 8. We can also write this symbolically in this way. V, the volume, is proportional to L cubed. Another thing I'm going to mention is surface area. Surface area is the total area of the outside faces or curved surface of a three-dimensional shape. And surface area is going to scale up in the same way as area, that is with the square of the linear scaling factor L squared. So let's look at that here. If the length of the side of my small cube here is 1, then the area of one side of the small cube is 1, since area is length times width, so this would be 1 times 1 is 1. And the small cube has 6 faces, so its total surface area is 6, and I can write that as surface area SA is equal to 6. So now if I look at my large cube, that's going to go up, the surface area will scale up like L squared, and you can see that each face of my large cube fits 4 faces of my smaller cube, so each of these has a surface area of 1 for a quarter of the side, so each side of my larger cube has a surface area of 4. And there are 6 sides, so its total surface area is going to be 4 times 6, or L squared times 6, which is 24. Let's look at an example of making a model. An architect wants to make a model of a house to show to a client. The model will have a linear scaling factor of L equals 1/40. If the footprint of the full-size house is 2,000 square feet, what is the footprint of the model house? Well, the footprint is going to be an area. It's just the area of the bottom of the house. So then it's going to be proportional to L squared, or scale like L squared. Then the footprint of my model is going to be 2,000 square feet times L squared, so 1/40 squared, and if I put that in my calculator, that's going to be 1.25 square feet. So the footprint of the model is going to be 1 1/4 square feet. In this section, I also want to talk about the language of growth, enlargement, and decrease. Two things are frequently compared by looking at percentages. We can say, for example, that a cereal has 40% more fiber than the leading brand, or that an item costs 15% less than retail at a club store. So we want to define precisely what these types of phrases mean so that we can understand these claims. So here I've got a list of the meanings of some phrases about percentages. So if I say that, for example, B is X percent of A, or X percent as large as A, that means that B is equal to X divided by 100 times A. If I say that B is X percent more than A, or A has increased by X percent, that means that B is equal to 1 plus X divided by 100 times A. If I say that B is X percent less than A, or A has decreased by X percent, that means that B is equal to 1 minus X divided by 100 times A. So let's look at some examples of uses of these kind of comparisons. First, let's look at a cost comparison. Streaming movies cost Netflix 10 times less than mailing them is the title of an article on Gizmodo.com. What does this claim actually mean? Well, it's not quite clear from the phrases that we've looked at what this means, but it seems like they are trying to say that mailing costs 10 times as much as streaming. Equivalently, we could say that the cost of streaming is 1/10 or 10% of the cost of mailing. And in general, you want to avoid using phrases like X times less than A, which can be confusing, and also X times more than A. It's also confusing. Now let's look at an example of an incorrect comparison. The Virginia National Guard has a program for at-risk teens called Commonwealth Challenge. The cost per cadet is $15,000 for the 17-and-a-half-month program, and they claim that the cost is 433% less than juvenile corrections. Can this be right? Well, according to what I just said about the meanings of percentages, if J was the cost of juvenile corrections, then this would mean that $15,000 is 433% less than J. So that is 1 minus 433 divided by 100 times J, or J is equal to $15,000 divided by 1 minus 433 divided by 100, which is equal to negative $4,505. But that can't possibly be right. We can't have a negative cost for juvenile corrections. So what are they actually trying to say here? Well, they must mean that juvenile corrections cost 433% as much as the National Guard program. So then, according to my meanings of phrases, that means that J is equal to 433 divided by 100 times 15,000. So then if I put that in my calculator, that means that the cost of juvenile corrections is going to be $64,950. So that makes a lot more sense for what they're trying to say here. That finishes up the section. These are the things you should know. You should be able to know the meaning of geometric similarity, so that two shapes are geometrically similar if they're the same shape, but they can be different sizes. Know how area and volume scale with the linear scaling factor L, and interpret the meanings of percentages and tell if a claim is reasonable.